So we can start. Let's talk again by Jonathan from Iowa State University. So please start.
Good. Thank you. Yes, so I want to thank Peter especially for making the connection with physics here with non-associative algebra, and that got me thinking. And this, what I'm about to present, is sort of the result of that. So this is my answer to the question, where are the non-associative algebras in physics? And this is being recorded, so I have to be careful what I say, but how would you feel if you were a group theorist and your subject was classified as other generalizations of number theory? Okay, but it doesn't tell you anything about the connection between groups and symmetry. Okay, so that said, I am not a big fan of a mathematical organization which classifies something I've been working on for almost 60 years now as other generalizations of groups. 20N05, I'm calling your name. So what I want to suggest in this talk is that just groups are all about symmetries, quasigroups are all about symmetry breaking. And then, what is symmetry breaking? Well, stuff. Any stuff is all about symmetry breaking. So that's what I like to do with this talk. So how are we going to do it? Here's the plan. Going to start with talking about quasigroups from general subgroups, and then bring in symmetry breaking in physics. I'll give you the standard example for that, the sombrero example connected with superfluids. And then we'll get into what are called either Goldstone modes or Higgs modes. You heard about the Higgs boson a little earlier today. I will show you how hot solids break Euclidean symmetry. That's one example. That will be very classical, so you don't need to be a quantum theorist to know that one. Second example will be the group SU2 in quantum chromodynamics in QCD. And again, very nicely, Cole mentioned that earlier on this morning, and how we always just see the left-handed side of things. What's going on there? Where does that come from? And then the final thing above the line will be about the local quasigroup F2, so just sort of reflection on S2 in antiferromagnetism. And you may not have heard of antiferromagnetism, but you've probably got one of these things, laptop with a hard drive, and antiferromagnetism is a critical technology to make sure you don't lose all your data, like I thought I was going to do a couple of nights ago. And then below the line, what does this mean as a research program for quasigroup theory and more generally for quantum quasigroup theory? Okay, so some of this will be very familiar to you. If you take a normal subgroup H of a group G and you take the quotient is a group. What happens if you take a subgroup that's not necessarily normal? Well, you just get in general, a right quasigroup structure. If you're lucky, it'll be a quasigroup structure, two-sided, on a transversal to H in G. The construction, we want to avoid choosing what an identity element is, but we still like to talk about loops. So if you just got two elements, U and V, in a quasigroup Q dot, we can define a loop, X plus Y, as X divided by V times U dividing into Y. and the identity element 0, the neutral element there, will be U times V. So you can do this for any pair of elements inside a quasigroup. You don't have to break symmetry by starting with a particular identity element. So then x times y, uv r plus of xv, r plus of uy, uv r plus of xy. It's in the coset of the stabilizer of u and the stabilizer of the element uv in the multiplication group G multiplied by r plus of x times y. Sorry? It's right multiplication in this loop. So it's a permutation which adds y to an element x. Or r plus of y would be the permutation that adds y to an element x. Okay, so here's the picture of what's going on there. So in this sense, we have the quasigroup Q as a quotient of the group G, and then just by this picture of projecting down, UV, we kind of fix that. That's our group H, and then we get the cosets of that subgroup that doesn't have to be normal. Okay, so that's the quasigroup theory. Symmetry breaking in physics. Example of superfluids. Well, this shows up in lots of technological situations. A superfluid is a fluid that doesn't have any viscosity to it. My favorite example of a superfluid is if you ever watched a flock of starlings, there's some nice videos of those, and then how they suddenly change direction and swirl around. That's modeled very nicely by the idea of a superfluid. So keep that picture there. And what kind of symmetry breaking is going on there? Well, the nice simple reduction, simple example, we have a global rotational symmetry. G S1 or U of 1 of C cross R about R, so a three-dimensional real space there. And then we have the famous sombrero picture, which is the classic way to present symmetry breaking. So for a complex number phi, think wave function, here's the potential energy, which only depends on the absolute value of phi. Hence we have the rotational symmetry. And if you're up here at the top of the hat, you have that circular symmetry. So that's the full symmetry that's going on. But physical systems like to move to reduce the potential energy. So they will drop down to this minimum here. And when that happened, they broke the symmetry. You no longer have the full circular symmetry. The only way, once you're stuck here, you're really down to no symmetry at all at any particular state here. And then there are like two dimensions you can move around here, but the one we'll think about will be keeping that minimum of potential energy, because there may be no more energy coming in there, and then you're just constrained down to that region. So that's the classical example of symmetry breaking. The states of lowest potential, they only have the trivial symmetry group, H equals 1, and the quotient is the S1, which you can think of as our quasigroup, has the broken symmetries. So that's the basic idea of broken symmetry. What would H be? Just a trivial group. Any particular state, if you stay there, there's no symmetry available to it. So what are these Goldstone modes or Higgs modes? So there are some weasel words here. Under appropriate technical caveats and conditions, we get the Nambu-Goldstone quote-unquote theorem. And here I'm being an obnoxious mathematician by putting these quotes around. This is a physicist's theorem, not a mathematician's theorem. Okay? Each broken symmetry generator, for example, we can going around on that bottom part of the sombrero picture, it determines an excitation or quasi-particle or collective mode. And historically, they were called Goldstone modes in condensed matter theory or Higgs modes in high energy physics. Gradually now that, as we learned more over the last, 50 years, 60 years on this, excuse me, the terminology has been refined. So this historical terminology does not always apply, will not always be considered correct in modern terminology. So I said there are lots of caveats going on here. It's not as simple as I'm trying to make it appear. If you want some kind of stability, well, you might need to go to what is called the thermodynamic limit for long-term stability. That's a big issue that I don't have time to get into in 20 minutes, but that's one of the key words to be aware of. And then also there are so-called inverse Higgs, and where you think you've got lots of different modes that you can go into, there it turns out there are dependencies amongst them. So you start out thinking you've got lots of Goldstone modes or Higgs, and then there are these inverse Higgs things that happen, and I'll give you an example in a minute, which actually reduce the number of primary modes that you are going to appear, good to have appearing. So that's usually when you have some kind of algebraic or analytical dependencies showing up. Okay, so without getting into quantum mechanics, let's see how solids break Euclidean symmetry. Okay, so here is a solid object. Okay, we are inside Euclidean space. So we got the special Euclidean group, R3 extended by SO3, and that in general is available at every point in space. So we can translate with R3, or we can turn around with the SO3, rotate around. So imagine that's the full symmetry happening at every point in our Euclidean space. That's the global symmetry. And there are Lie algebra generators associated with those. We'll use PIs for the translations, and the JIs are rotations about various axes. And in quantum mechanics, there are so-called notocurrents that are associated with those, and those correspond to the momentum and angular momentum operators. So the global symmetry of the space R3, local symmetry at every point. And we also have to add the time generator P0, which corresponds to the Hamiltonian, measuring the energy of the system. And then we have commutation relations. Commutator relation of Ji with Pj is I epsilon ijk pk. Epsilon ijk, it's just a sign representation of the permutation group on the indices ij and k. And this is for jk greater than 0, so we're not having j equals 0, the Hamiltonian here. And then the commutation relations for SO3 with I ijk jk. And of course, after the mathematicians talk on the algebras, this is the physicist's way of doing things. Yeah, John.
Are you using Einstein convention there?
Yeah.
That means there are two K's on the right-hand side, but no K's on the left, so you're supposed to sum over the K on the right-hand side.
Okay, so what happens when we have a solid? Well, if I move the right-hand side of this thing to the left, everything moves across to the left. So all the different points of this solid have lost their freedom to move. And basically, if I just get the center of mass and determine that, this one happens to be symmetrical, but that's limiting the symmetries that are available to all the individual points in the solid. So that's why stuff is sort of solid, why stuff all moves together, because of the broken symmetry here. And then the Higgs modes from P1, P2, P3 from the space translations, those are the phonons. So if I make a sound there, there's a sound wave. In quantum mechanics, there's this wave-particle duality. So the phonons are the particles that correspond to the waves that you probably just heard, there with the from the waves there. So the 3 Higgs modes there. Why only 3? Well, this other thing going on here is because of this relations between the J's and the P's, there are inverse Higgs which eat the 3 rotational modes Ji. So that's the sense then in which solids break special Euclidean symmetry. So kind of a classical version of the symmetry breaking, and you see this inverse Higgs thing happening because of this algebraic relation that's holding there. Okay, coming back to what Cole mentioned in her talk, the group SU2 in quantum chromodynamics mixes up and down quarks as an internal symmetry. You have the left and right Weyl spinors that you mentioned. Those have parities because they transform the same under the spatial rotations, but oppositely under the Lorentz boosts, and a switch by parity. So the vacuum state, the lowest energy QCD vacuum state, it breaks the SL2L cross SU2R symmetry, just leaves the subgroup SU2 invariant. And the critical observation here, where the quasigroup theory comes in very nicely in this example, is that this SU2L cross R, that's the multiplication group of the group SU2, and the invariant part is the inner multiplication group of SU2. So in other words, where the Goldstone pions, the Goldstone modes are the pions, and then this symmetry breaking is exactly described by quasigroup theory. So this is really what the Germans would call Paradebeispiel for what we're doing here. And physicists already know about this. This is the so-called coset construction of Vess and Zumino and others. Okay, we can also get local quasigroups rather than full global quasigroups appearing. So let's quickly look at antiferromagnetism. So if you've got a lattice in any dimension that you're in, consider electron spins at each lattice point. Ferromagnetism is where all the spins are in the same direction. So those tiny little atomic magnets or electronic magnets, they all join together and you get a macroscopic magnet. But the antiferromagnetism is where the spins are always, adjacent spins always in the opposite directions. So an antiferromagnet, what's called an AL state, has 2 distinct sublattices. So you see this most easily on the one-dimensional example with the Ising model. Ferromagnet, they're all lined up the same. The antiferromagnet, they keep alternating all the way through. And on the cubic lattice, where at each point you could get any direction for the axis, the global symmetry is SU2. If you choose a single direction for the antiferromagnet, that breaks the symmetry, and then the reigning symmetry is U of 1, and they're the local quasigroup. It's SU2 quotient U of 1, so it's S2, the sphere, and we know that can't sustain a global quasigroup structure, but we have a local quasigroup structure. Okay, so there's a bunch of examples of symmetry breaking for you. So what does it mean for somebody working in quasigroup theory? Well, it opens up a research program, and I would extend this to quantum quasigroups. So here's a single picture to quickly tell you what a quantum quasigroup is. Let's look over on the right-hand side. What do Hopf algebras do? Well, you either have like a Lie group or a global group, or you can just work locally with a Lie algebra. And then the Hopf algebra is a nice way to combine those two things without having to do differential geometry. Everything's done in a nice algebraic fashion. Corresponding to a Lie algebra, you get the universal enveloping algebra as the Hopf algebra. Okay, if we start here with groups, Hopf algebras are a generalization of groups. Groups are Hopf algebras in the category of sets. But quasigroups are another generalization of groups where you relax the associativity requirement, and then quantum quasigroups unify quasigroups and Hopf algebras. So the program then developed the theory of quantum quasigroups as a general setting for the study of symmetry breaking phenomena. Certainly going to bring in web geometry, Marikatan forms, all that good stuff from web geometry. And that's already showing up a little bit in some of the physicists' literature on symmetry breaking. Invoke supersymmetry if we don't just want to talk about bosons, sort of forces, but we also want to talk about electrons and stuff like that. Well, we can combine that to do supersymmetry breaking, and there, rather than the Goldstein modes, they talk about Goldstinos. And use quasigroup theory to quote unquote repair broken symmetry. Let's say you don't know what the big global symmetry is. You've just got the stuff that you're doing experiments with. So you know the local symmetry that your stuff satisfies. You know what the stuff is. How can you reconstruct the global symmetry out of that? Well, you use all these wonderful constructions we have in quasigroup theory for creating, for example, universal or relative multiplication groups, autotopy groups. So all this good stuff that we have in quasigroup theory, all these groups we have available to us, those then will give us a global picture if we're only working and only seeing the local symmetry and the stuff that we have with the quasigroup structure. Okay, thank you.
I have two questions. Okay. So the first one is, I think I missed what is the quantum quasigroup.
Okay, so the quick story was it's a common generalization of Hopf algebras and quantum quasigroups. So there are two, if you're familiar with Galois operators in Hopf algebra. Okay. So you get a right and a left kind of Galois operator, and those both have to be invertible. That's a quick definition. So, for example, in a classical quasigroup, if you take the pair xy to x star y, where star is your quasigroup multiplication, that's like the left operator, and that's invertible if and only if star is, or in the other side, xy goes to x star y, y. Yeah. So if you have a set and a q, and then q squared, these two operators, you have a binary product. If these two operators are invertible, then that tells you the binary product is a two-sided quasigroup. So it's just a more general version of that.
The second question is it usually in the way they describe particles and symmetry is through a principal bundle, right? So you have
Sorry, through?
through a principal bundle, right? Your group of symmetry is the thing on top of the manifold, the ground manifold.
Yeah, yeah, or yeah, let's go back to that picture then, right at the beginning.
Right. So if
Just let me find the home key or
my question there, if you break your symmetry, do you need a theory of quasi-group fiber bundle, something like that?
in some sense, yes, but you automatically have this structure. So that's what this picture is meant to suggest. That anytime you have a quasi-group, yeah, it's like you've got the bundle for the H acting on there.
This is
Yes.
automatic because of the portion you have without the normal.
So correct. Yes.
The
Yes. Yes.
geometry doesn't get completely crazy.
No.
It
No.
does.
No.
I can see the question outside from the.
Yeah. Ben, yes.
A general question. So, do I get it right that quasi-groups are the mathematics behind symmetry breaking? So if we have symmetry breaking in nature, we have a quasi-group in the background.
That is the general message. Yes.
This should also mean that non-associativity is the mathematical source of symmetry breaking, and that basically for theories with symmetry breaking, we should have some non-associative theory. For example, in field theory, then there should be some non-associative quantum field theory describing symmetry breaking, correct?
In general, yes. In the QCD example I showed, the quasi-group was actually a group, SU2, which is, of
Yes.
course, associative.
Okay, so in the special case of QCD, we can keep associativity, but in general, symmetry breaking is a hint towards non-associativity.
Correct. Yes. Yes.
Okay, so that means if I were out to look for a non-associative quantum theory, I should study symmetry breaking processes more in detail and look for other signs of non-associativity, maybe.
That's my proposal here. Yes.
Yeah, so
Okay,
rather than saying there's
you
no-
can steal it from me.
rather than saying there's no non-associativity in physics, you're saying there's occasional associativity in physics.
Yes. 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 Very well said.
So I didn't hear this. What did he say?
Oh, rather than saying there's no non-associativity in physics, there is occasional associativity in physics.
Ah, okay. So inverse the argument. So it's about okay. Just an additional question. So why don't we see other signatures of non-associativity then in physics? Didn't we look correctly?
Maybe. Maybe.
Okay, maybe. But thank you very much for this very inspiring and interesting talk.
Thank you, man.
Yes, I would add very quickly, Lie algebras are used in physics all the time and they're non-associative.
People don't
True,
like to
but,
admit that. People don't like to admit that.
Yes, absolutely. And they should because they're everywhere.
I have a colleague who
true, yes.
organizes a seminar on algebra, and the very first word he says is, "We will study associative algebras." But he does do
But
Lie algebras a lot, so there you go.
But
John,
for Lie algebras, we have an associative product in the background. We use the commutator to define the Lie product, and then we still have an associative product. And it's a little bit like with special Jordan algebras. We always have an associative product in the background. This here seems to be more intrinsic non-associative, if I may call it like this, but maybe this is
yeah.
very picky, I admit.
When you subtract integers, it's not associative.
Also true, yes. Yeah, right. I admit it.
Remark in this context, and I think it's one of the Bourbaki volumes, I think, on algebra. In the historical portion, there's a single line quote, something to the effect of, there are, of course, it is of course possible to consider non-associative algebras, but nothing very interesting occurs in that.
There we go, 2005, the generalizations of groups.
So. Very short. Really.